What's up, boys and girls and everyone else? This is another science video lesson episode for you. And for this episode, we will be going to talk about an introductory topic for gas laws, the properties of gases, and the kinetic molecular theory. Come join me today as we go over these measurable properties of gases and the kinetic molecular theory in this episode, Measuring Gases. Alright, so here we are in our video lesson topic for this episode. So we have measuring gases. So in this topic, we were going to discover, this is an introductory topic for the upcoming video lesson, which is called the gas laws. Alright, so in that video lesson next week, we were going to encounter several gas laws, and those gas laws will use the properties of these gases that we were going to talk about this in this episode. Alright, so before we go to the concepts behind this topic that we have right here, special shout out to my grade 10 students who are currently watching this lesson that I have right here. So I hope you will learn from this one and practice, okay? Practice more. Okay, in order for you to understand what is on the lesson that we have right here. Alright, so with that, let's get started. Alright, so the measuring or the properties of gases are governed with certain principle, which is called the kinetic molecular theory. So by the way, we were going to talk only gases here. Alright, so we were going to talk about one state of matter here, the gases. So as we all know, gases are compressible, alright? Compressible, and compared to liquid and solid, the distance of the molecules in this state of matter is very, they are separate at a great distance. Okay, the molecules in this state of matter is separated at a great distance compared to the liquid and the solid matter. Alright, and also gases also takes up the shape of the container in which it is placed into. Alright, so that is those are some characteristics of this state of matter that we were going to talk about in this episode. Now, in this particular principle, it explains why gases behave the way they are observed. Okay? And also, this principle talks about the ideal gas particles. Alright? So, only the ideal gas particles. So, the parameters that you have right here, these 4 parameters that you have, talks about only the ideal gas particles. Okay? But in reality, the measurement and the values that are obtained, okay, that are obtained in measuring these gases are somehow deviated from the ones that we have right here in an ideal environment, okay, in an ideal situation. Okay, so for you not to be confused about this one, so we will going to use the only ideal situations that we have right here. All right, so number 1, so the first parameter that we have here in the kinetic molecular theory is that the gases are so small. Okay, most of the time they are assumed as 0 volume. Okay, so because gases are so small, okay, molecules of gases are so small, so we thought that they have 0 volume. Okay, so that's the first assumption that we have right here. The second parameter is in constant. Okay, gases moves in constant straight line motion. All right, so gases always moves in a constant straight line motion, that the one that you have over here. Okay, now the third parameter is it experience elastic collision. So what do you mean by elastic collision? These are collisions that are not sticky. Okay, these are collisions that are not sticky. When the two molecules collide, all right, so when the two molecules collide in this manner, when the molecules collide here, they change direction, and also it changes the kinetic energy, all right, of those two molecules. So that is the elastic collision that we are talking about here. So at the end of the day, no energy is lost. Okay, no energy is lost, and the total kinetic energy of the system is conserved. Alright, so the total energy of the system is conserved. So there's also no attractive or repulsive force that works towards this molecule. So that is why these molecules that you have right here experiencing only elastic collision. Alright, so that is number 3. And the fourth and final parameter of this kinetic molecular theory that we have right here is the gases have an average kinetic energy that is proportional to its absolute temperature. Now, when we talk about absolute temperature, it is not in degrees Celsius, it is not in degrees Fahrenheit. It is in Kelvin. Alright? It is always measured in Kelvin. So, in the fourth parameter, in gases, as the temperature increases, the kinetic energy of these molecules in this state of matter also increases. So they are directly proportional to each other. Okay, so that is the fourth parameter of the kinetic molecular theory that we have right here. Alright, so again, these 4 parameters that you have right here only exist in ideal conditions. Alright, they are only existing in ideal conditions. So most of the time in realistic calculations, these 4 parameters is somehow deviated. Alright, it is somehow deviated in some cases. Okay, so we were going to use the idealistic condition of in which these gases are placed upon. Okay, so that is the kinetic molecular theory. Alright, so to ask, okay, this is the question that we were going to ask ourselves. What are the measurable properties of gases? Okay, so if you do have any idea before we go to the concept that we have right here, just write your comments in the comment section below this video. Alright, so what are the measurable properties of gases that we can use in the next video lesson that we will have? The gas law. So what are these measurable properties? Okay, so there are 4 of them. Okay, there are 4 of them, and most of them, alright, most of them follows what is stated in the kinetic molecular theory. Alright, so we have the first one, pressure, the second, volume, then we have the temperature, and we have the amount of gases. Okay, so all of these 4, we were going to discuss each and every properties that we have right here, and we will somehow find its effect, okay, when we go now to, or when we go to the topic that we have in the gas laws. Alright, so these are the variables. We have volume, temperature, pressure, and the mole here, the mole that you see on this picture is the amount of gas. Okay, is the amount of gas. Again, we will stick only on one state of matter, which is the gas. Okay, so with that, let's start with the pressure. Alright, so what is pressure? Okay, so this is the first measurable property of gas. And when we talk about gas, pressure is the number 1 property that we should take note of. Alright, so what is pressure? This is the measurement of force per unit area. Alright, so pressure is the measurement of force per unit area, and the pressure which is exerted by the gases and the pressure which is exerted by the gas is the force exerted by the gas on the walls of the container. Okay, so if you don't have any idea, so if you take a look at the balloon, alright, so if you take a look at the balloon, once you inflate that balloon, okay, so from a clumsy rubber, it becomes a hardened rubber once it is inflated. So, meaning to say that the walls of your balloon is where these molecules tend to exert their force. Okay? When this molecules exerts force on the walls of this balloon, okay, therefore the pressure is measured. Okay, so there is a pressure that is exerted on those walls. Okay, so in order to get the pressure which is exerted by the gas on the walls of the container, you need to divide it by the surface area of the container itself. Okay, so you can divide it by the surface area, and then that's the time that you will get the pressure which is exerted by the gas in the walls of your container. All right, so again, pressure is force over area. Okay, so what are the things that we can take note here? Okay, So as you can see here, which do you think? Okay, which shoes do you think creates most pressure? Alright, so which shoes do you think creates the most pressure that you have right here? So you can write it down in the comment section below this video. Okay, so now, in order to select that one, so girls can, girls are familiar on this, okay? So probably their answer will be this shoe. Alright, so these shoes that you have right here, the heels, okay? Because the heels have a very small area, alright? And the force that you are exerting is large. Okay, the force that you are exerting here are large, and it is exerted in a very small area that you have right here. So that is the reason why when you wear heels, it is somehow painful to your feet. Okay, so unlike this one that you have right here, it has greater force, but it is spread or it is distributed on a large area. Okay, so including this one as well. Okay, including this one. So this is the shoe that is wear by some people in walking on ice. Okay, so this is a type of shoe that is used in walking on snow, something like that. So this one. Okay, again, it has a large area, alright, in which the pressure or the force that is exerted is distributed. Okay, so the one that creates most pressure is these heels that you have right here. Okay, so now in order to understand how this force and area interacts and becomes pressure, so we must always take note that pressure always exerted or pressure exists when a force is exerted over a certain area. Now, if force is acted over a large area, okay, if a certain force is acted over a large area, then the pressure is very small. Okay, so if the area is large and the force is somehow exerted over the large area, then the pressure is small. Okay, so meanwhile, alright, meanwhile, if the force is acted on an area, okay, if the force is greater but the area is smaller, okay, then therefore the pressure is greater. Okay, so the pressure is greater. So technically speaking, that the force and the pressure is directly proportional to each other. Okay, and the area, alright, the area and then the pressure, alright, so the area and then the pressure is inversely proportional to each other. So the greater the area, the lesser the pressure. The smaller the area, the greater the pressure. So they are directly proportional or inversely proportional to each other. So those are the things that you need to take note about these two variables that we have right here, the force and then the area. Okay. Alright, so we have here the barometer. So in measuring the atmospheric pressure, we need to use a barometer. So this is the barometer invented by Torricelli. Alright, so way back in 1800, something like that. Okay, so this particular barometer is somehow an improvised form of the barometer. Unlike that what we have seen in our modern devices, barometers in the modern devices is different from the one that you have right here, because the barometer right here is using a mercury. All right, so the grade that you see here is the mercury. All right, so that is why the very familiar measurement of pressure, atmospheric pressure during that time is in millimeters of mercury. Alright, in millimeters of mercury. Now, what we have right here is a barometer, which is an improvised, and we have right here a mercury, which is placed in a petri dish over here. And we have a test tube inverted, and inside the test tube there is a certain level of mercury measured in millimeters. Okay, measured in millimeters, and exactly it is exactly measured as 760 millimeters from this point up to this point. Alright, to the surface of the mercury on the petri dish that you have right here. Okay, now there's a vacuum or there's an air on inside the glass tube. Now, once the atmospheric pressure pushes this mercury, on the Petri dish, it will push this mercury inside the glass tube upward. Alright, so it will push the mercury inside the glass tube upward, and it will change the measurement. Okay, definitely. Okay, so from 760, probably it will increase. Now, if the atmospheric pressure is very low, then therefore this glass tube that contains the mercury will also push the mercury downwards. So it decreases the pressure. Alright, so it decreases the pressure of mercury inside this glass tube. So definitely the value of this measurement, the value of this 760 will definitely decrease. Okay, if the atmospheric pressure suddenly decrease. Okay, so that is the barometer. This is the device that uses, or this is a device that is used to measure atmospheric pressure. Okay, now the barometer varies. Okay, the measurement of your barometer varies in terms of altitude. Okay, so when you measure the pressure at different altitude, it will vary differently. So for example, as you increase in altitude, okay, so when you go to Baguio, alright, so when you go to Baguio, so Baguio has a higher altitude, okay, because it is above sea level. Okay, that area is above sea level, not only in Baguio but also in Tagaytay. Okay, Tagaytay City. So that is higher altitude, but the pressure on those areas are less. Alright, so the pressure on those areas are less. Unlike here in Manila, we are on the somehow sea level. Alright, so we are somehow on the sea level, so the pressure here is greater compared to those area. Okay, so altitude is inversely proportional to your pressure. Okay, so as the altitude increases, the pressure decreases, vice versa. Okay, so we have right here, how does the force over area on your pressure is applied on the atmospheric pressure. So suppose we have here the column of air. Okay, so this is the column of air that you have right here. Now, as you go, alright, so as you go to the surface of the earth, as you move through the surface of the earth, the atmospheric pressure increases. So on this part, the atmospheric pressure here, alright, so the atmospheric pressure here is increasing. And therefore, the area becomes less and less. Okay, so as you can see, as you go up on the atmosphere, the area or the column of air, the area of that column of air increases. So as you can see here, the area increases, and when you go to the surface of the earth, the area decreases. So definitely, as the area decreases, the pressure increases. Okay? And as the area increases, that you have right here, the pressure, the atmospheric pressure, alright, the atmospheric pressure on this area decreases. Alright, so that is the the thing here. Okay, because the area over here is increasing. Okay, so what happens to the molecules of air as the area increases? So the molecules of air separates at a greater distance. Okay, unlike what you have over here, since your area is decreasing, okay, so the molecules are somehow not separated at a greater distance. Okay, the air molecules on this area, on the surface of the earth, is not separated at a greater distance, unlike on the higher atmosphere, like stratosphere, mesosphere, okay, and even the exosphere. Okay, the thermosphere, the ionosphere, the air molecules on those areas are greatly separated. Okay, they are greatly separated, so that is why the pressure there is somehow lesser compared to the one in the surface. Okay, so those are the things that you should take note of about the atmospheric pressure. Alright, so these are the units of pressure that we were going to use in our in this variable. So the first one, we have Pascal, in honor of Pascal. Okay, so we have atmosphere. Okay, so we have Torr. Okay, Evangelista Torricelli. Alright, so we have millimeters of mercury. Okay, so we have here the millimeters of mercury. So just like what I've discussed earlier, so millimeters of mercury was obtained on the improvised barometer used by Evangelista Torricelli. So that is why called millimeters of mercury. So the improvised barometer that you have encountered earlier. Okay? So Pascal. Okay? So Pascal, atmosphere, torr, and mercury. So these are the conversion factors that you need to take note. Okay, so if you encounter some problems that requires you to convert every pressure measurements that you see there, so these are the conversion factors. So 1 atmosphere is equivalent to 760 torr. 1 atmosphere also is equivalent to 760 millimeters of mercury. 1 torr, all right, is equivalent to 1 millimeters of mercury. More so, we have the 1 atmosphere is equivalent to 101,325 Pascal, and 1 kilopascal is equivalent to 1,000 Pascal. So these are the conversion factors that you should take note of when you are converting certain units of pressure. Alright, so let's try answering this one. Okay, so suppose we have an atmospheric pressure at the summit of Mount McKinley, which is said to be 606 millimeters of mercury. Okay? And what is the pressure of that 606 millimeters of mercury in atmosphere and in kilopascal? Alright, so let's jump right into it and let's solve for this answer, atmosphere and kilopascal. Okay, so we have right here 606 millimeters of mercury. Okay, so we will convert it into atmosphere and kilopascal. Okay, so what do you have right here? So we have 606 millimeters of mercury. Okay, so multiplied to... Okay, so in this case, we will going to use the basic mathematic concept called dimensional analysis. Okay, if there's a certain unit that are similar, we're going to cancel them. Okay, what is left behind is the unit that we are looking for. Okay, so we have 606 millimeters of mercury, and over here, all right, so over here is the conversion factor. So how many mercury or how many millimeters of mercury are there in 1 atmosphere? So we have here in 1 atmosphere, how many millimeters of mercury? So we have here 760 millimeters of mercury. Alright, so let me compute. So how many atmosphere do we have right here? Okay, so how many atmosphere? So we have to cancel this one since they are similar. So 606 over 760. Okay, so did you have the same answer? Okay, so that's the answer that we have right here is 0.797 atmosphere. Okay, so that is the answer. So 606 millimeters of mercury is equivalent to 0.797 atmosphere. Okay, so now if you want to compute it directly to kilopascal, okay, so kilopascal, so we have multiply, okay, 1 atmosphere over here is equivalent to how many Pascal? So we have 101,325 Pascal. And that Pascal will be converted into kilopascal. So, okay, so 1,000 Pascals is equivalent to 1 kilopascal. Okay, so dimensional analysis, cancel all the similar units that you see. Okay, so that's the time that we can compute now. So 606 over 760, okay, times 101,325, right? And divided by 1,000. Alright, so the answer here is how many kilopascal do we have right here? Okay, so we have 807.9 kilopascal. Alright, so that is 800, why 1,000? Why did I divide 1,000? Sorry. Okay, so let me repeat the calculation. I divided into 100. Okay, so again, 606 over 760. Okay, times 101,325. Okay, divided by 1,000. Okay, so the answer is 80. Alright, 80.79 kilopascal. Okay, so 606 millimeters of mercury is equivalent to 80.79 kilopascal. Okay, so that is the answer to the first problem. So did you get the same answer? Alright, so do you have the same answer as mine? So let me know in the comment section below. If you have confusion, if you do have question, let me know. Okay, so the next one. Okay, the second problem that we have right here, the column of mercury in a barometer is 745 millimeters above the mercury reservoir. Okay, and at the bottom. Okay, what is the atmospheric pressure in pascals? Okay, so these are the units, or these are the values that we need to convert into Pascal. Okay, so we have 745. The problem was 745 millimeters of mercury. How many pascals is that value is equivalent to? Okay, so we have 745 millimeters of mercury times. Okay, so times, we have 1 atmosphere is equivalent to 760 millimeters of mercury. Okay, times, again, another conversion factor here, 1 atmosphere is to 101,325 Pascal. Okay, so let's cancel all the units that are similar. Cancel, 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 and we left with this unit. So, what is the answer? How many Pascal? So, we have 745 over 760 times 101,325. Okay, so the answer will be 99. Okay, 99,325 Pascal. Okay, so that is the equivalent of 745 millimeters of mercury. Okay, so that is the equivalent of 745 millimeters of mercury to Pascal. Okay, so these are the conversion factor, okay, that you need to take note about, learn about this variable called pressure. All right, so up next is the next variable that we have right here, which is called the volume. What is volume? So the volume of the gas is equal to the volume of the container. So this is one of the impressive characteristics, or the one of the characteristics of this state of matter, the gas. While being compressible, it can also take the shape of the container. So that is the volume. Alright, so the volume of the gas is somehow equal to the volume of the container. Now, most of the time in the gas law calculations, we always use its basic unit, which is called liters. Alright, so most of the time, yan, volume is the basic unit of volume is always in form of liters. Alright, but most of the time, or sometimes, there are some units that are used, okay, and you need to convert them into its basic unit, which is the liter. So these are some units that you should take note of in terms of volume. Now, suppose you consumed 1 cubic meter of water. So how many liters is that? Okay, so how many liters is that 1 cubic meter is equivalent to? So we have 1 cubic meter is equivalent to 1,000 liters. So meaning to say that you consumed 1,000 liters of water. Alright, more so, 1 cubic meter is equivalent to 1 million cubic centimeter. Okay, in some cases. Okay, so 1 liter is equivalent to 1,000 milliliters. I think you know that one already. And 1 liter is also equivalent to 1,000 cubic centimeter. Okay, so 1 liters is equivalent to 1,000 cubic centimeter. And more so, we have 1 milliliters is equivalent to 1 cubic centimeter. Okay, so these are the conversion factors that you should take note of when you are dealing with units of volume. Okay, so let's try and take a look. So suppose that you have a so suppose your water bill arrived and you analyze your water bill and you found out that you consumed around 500 cubic meters of water. Okay, you want to know how many liters of water you consumed on that month. Okay, so that is very simple. Once you are very familiar with this conversion factor that you have right here, there will be no problem for you converting this one that you have right here into liters. Okay, so we have it. We will going to use dimensional analysis here. Okay, dimensional analysis is very important in conversion problems that like that we have right here. Okay, so we have 1 liter. All right, so 1 liter is equivalent to how many cubic meter? All right, so or somehow 1 cubic meter is equivalent to 1,000 liters. Okay, so how many liters is that? Okay, so how many liters is that? So 500 times 1,000. So that will be 500,000 liters. Okay, so meaning to say, in 1 month, you consume 500,000 liters of water. That is equivalent to 500 cubic meters. Okay, so suppose, another question. So suppose you bought a 1.5 liter Coke. Alright, so 1.5 liter of soft drinks. Right, so 1.5 liter. Now, you want to know how many cubic centimeters is that. Alright? Right, so you want to know how many cubic centimeter is that. Okay, so let's go back to the conversion factor and find out. So, in 1 liter, there is 1,000 cubic centimeter. Alright, so let's punch this value here. So, we have 1.5 liters times. Alright, so in 1 liter, there is 1,000 cubic centimeter. Again, we can cancel the similar units and we have 1.5 times 1,000. That is 1,500 cubic centimeter. So, you bought a 1,500 cubic centimeter soft drinks. Okay, so soft drinks bottle. Okay, so these are some sample computations about the volume. Okay, so up next is the next variable that we have right here, our next measurable property called temperature. Expressed in 3 units. So we have degrees Celsius, degrees Fahrenheit, and there's no degrees in Kelvin, so Kelvin only. Alright, so what is temperature? This is the average kinetic energy of the molecules. Okay, so this is the average kinetic energy of the molecules in your system. Okay, that is what we meant by temperature. And the greater the energy, alright, so the greater the kinetic energy, the greater the temperature. That's the thing that we have right here. Now, however, in gas laws that we were going to talk about next week is using only one kind of unit, and that is in Kelvin. Alright? So it uses only one unit called Kelvin. So that is capital K. So the one that we have right here. Okay, so if there is some cases, there are some cases that the unit is the unit used is in degrees Celsius. You need to convert that one into Kelvin. Okay? So in measuring the temperature of the gas, okay, we are not using the degrees Celsius, we are not using the degrees Fahrenheit, but we are going to use we will going to use here Kelvin. Okay, so in that case, you need to learn how to convert these units into the required unit that we have on your gas laws. Okay, so we have right here the absolute temperature, or the absolute temperature in Kelvin is in 0. Okay, so the 0, which is the absolute temperature, so in Kelvin, is equivalent to negative 273 degrees Celsius. Okay? And negative 459 in Fahrenheit. Meanwhile, the 0 degrees Celsius, alright, so the 0 degrees Celsius is the freezing point of water. Okay, the freezing point of water is somehow at 273 Kelvin. Okay, and 32 degrees Fahrenheit. While the boiling point of water, which is 100 degrees Celsius, is equivalent to 212 degrees Fahrenheit, and that is only 373 Kelvin. Alright, so that's the boiling point of water. This is the freezing point of water, and this is the boiling point of water. Okay, so now these are the units, or these are the formulas that you're going to use in this calculation. So later I will revise the formula that you have right here for you to easily understand and easily manipulate, okay, this formula in order to convert Celsius to Fahrenheit, Fahrenheit to Celsius, or even this one. Okay, so later we will have a sample problems related to that. Okay, now these are the things that you should take note of. Okay, when you are on a country that uses Fahrenheit, like US, okay, in United States they are using Fahrenheit, okay, degrees Fahrenheit rather than degrees Celsius. But most of the countries in this planet uses degrees Celsius, only in US. All right, so 0 degrees Fahrenheit is somehow based on the description, it is somehow really cold outside. Okay, it is somehow really cold outside. So when we talk about 0 degrees or 100 degrees Fahrenheit, so it is somehow really hot outside. Okay, based on the description. Okay, now when we talk about Celsius, 0 degrees Celsius is somehow not too cold. All right, not too cold and not too hot. All right, so somehow it is fairly cold outside. Okay, now when you are in a 100 degrees Celsius temperature, you are dead because your water in your body starts to boil. Okay, so that is 100 degrees Celsius. And more so, okay, more so that we have right here, we have degrees Kelvin, or rather, sorry for that, in Kelvin. Okay, 0 degree or 0 Kelvin is you are dead. 100 Kelvin is also dead. Okay, so because the 0 Kelvin is the absolute zero that we are talking about, in which the molecules, all right, the molecules on your gas, liquid, and solid tends to stop. Okay, this is where the molecules tends to stop moving. That is the zero or absolute zero. Okay, the 100 Kelvin is also somehow very cold. Okay, that is somehow very cold, the 100 Kelvin. So you are presumed dead when the temperature is 100 Kelvin. Okay, so these are the descriptions of the temperature, okay, based on how they are described, okay, by some people. Okay, now okay, let's try converting the following things that we have over here. Okay, now first thing that we have right here is when you are converting, okay, when you are converting degrees Celsius to Fahrenheit, okay, all you need to take note of is you will multiply it first. Okay, so the degrees Celsius, you will multiply it first with 1.8. Okay, then subtract it with or add 32. Okay, after. Okay, so again, multiply the degrees Celsius to 1.8 and add 32 after. Okay, now when you are converting degrees Fahrenheit to Celsius, so divide, all right, so rather, before you divide, minus or subtract 32 from the degrees Fahrenheit, then divide 1.8. Okay, so again, subtract 32, then divide 1.8. Okay, so that's how you convert degrees Celsius to degrees Fahrenheit to degrees Celsius. Okay, so let's take a look at this problem that we have right here. So we need to convert 837 degrees Kelvin to Celsius. So this is very easy. Okay, so the formula that we will have right here is degrees Celsius plus 273 is equal to Kelvin. So if you reverse that one, if you reverse that one, you will need to subtract 273 from this. Alright, so you need to subtract 273 from this. So what will happen here is okay, so degrees Kelvin to Celsius, so 800. Okay, so degrees Celsius is equal to 837 minus 273. Okay, so 837 minus 273, so that will be okay, so that will be, that is in Kelvin, so degrees Celsius will be 837 minus 273. Okay, that will be 564. Alright, 564. Okay, degrees Celsius. Okay, so that is 837 degrees Kelvin that you have right there. Okay, next one, we have 21 degrees Celsius. Okay, so we have 31 degrees Celsius. So what is the equivalent, okay, value on that on Kelvin? So again, we will going to use this formula over here. So we have degrees Kelvin is equal to 21 degrees Celsius plus 273. So the unit or the value that we got from this calculation is, so we have 294. Okay, so 294 Kelvin. Okay, so that is the answer to the second question. Okay, let's take a look at number 3. Okay, so let's take a look at number 3. So 88 degrees Fahrenheit to degrees Celsius. Okay, so we will going to use this okay, this one in order to convert that one into degrees Celsius. So we will going to multiply 88. Alright, so 88 degrees Fahrenheit rather minus 32. Okay, and afterwards divided by 1.8. Okay, so this one. Okay, so 88 minus 32, so that will be 56. 56 over 1.8, so that will be 31. Okay, so this 88 degrees Fahrenheit is equivalent to 31 degrees Celsius. Alright, so that is 31 degrees Celsius. Okay, so did you get the same answer? Okay, so let me know in the comment section below if you got the same answer as mine. Okay, so we have another one, 154 degrees Fahrenheit to degrees Kelvin. Alright, so why do I always say degrees? Okay, so 154 degrees Fahrenheit to Kelvin. So again, we will going to use this formula over here. Alright, so 154 degrees Fahrenheit minus 32. Okay, divided by 1.8. Okay, so 154 minus 32, that is 122. 122 over 1.8. Okay, so that will be 67.77. Okay, so that will be the answer there. Plus 273. Okay, so the answer is 340. Okay, 0.8 Kelvin. Alright, so 340.8 Kelvin. So that is the equivalent of 154 degrees Fahrenheit to Kelvin. Okay, so that's the computation there. Okay, so if you have a confusion, let me know in the comment section below, okay, about this one. So that is for the temperature. So up next is the fourth and final property of gases that we have right here, which is called the amount of gas. Alright, so we have here the amount of gas. And what is the amount of gas? Okay, so this is literally the number of molecules or atoms or ions. Okay, so since we are dealing with gas, so most of the time we will going to use molecules. Alright, so the quantity of gas is expressed in moles. Okay, so this is the basic unit of number of molecules, number of atoms, number of ions, etc., etc. in terms of amount. Okay, so they are used, or the unit of measurement there is moles. Okay, now the unit of mass, such as in gram, should be converted into moles. Okay, so suppose that you have encountered a certain gas that is measured in grams. Alright? That is measured in grams. Now, in order for you to find out how many molecules does that particular gas contain, you need to convert it into moles. Okay? Now, in order to convert it into moles, this is the basic formula in order for you to do that. Okay, so number of moles is equal to the mass of gas and the molar mass of gas. Okay, so molar mass is obtained. Okay, molar mass is obtained as the mass of the given substance divided by the amount. Okay, the amount of that substance. Okay, so that is the definition of molar mass. So most of the time, the molar mass, okay, so the molar mass is obtained, okay, you can see molar mass of your gas in the periodic table. Okay, so the unit of molar mass, okay, so the unit of molar mass is grams per, alright, so grams per mole. Alright, so the mass of the gas is grams. Okay. Now, with the help of our trusty periodic table, we can easily find the molar mass of your certain gas. Okay? So again, we are looking for the gas only here. Okay? We will not look for any kind of element, or we will not look on any kind of element that is not a gas. Okay? So, number of moles, okay, of that gas is obtained using the mass of the gas divided by the molar mass of your gas. Okay, so let's take a look on this. Okay, there's no conversion factor here. Okay, there's no conversion factor here. All you need to have here is your periodic table. Make sure that you have the atomic weight. Alright, so atomic mass of the element must be found on that same periodic table. Okay, so okay, in order for you to find out how to have this one, so let's have some sample problems regarding this concept that we have right here. Suppose we need to compute for the number of particles in the following gases that you have right here. Now, number of particles and number of moles are the same. Okay, they are the same. Okay, so don't be confused on that. Okay, so we have number 1, 10 grams of chlorine. Alright, so we have 10 grams of chlorine. So, what is 10 grams of chlorine all about? Okay, so we have the formula earlier. Okay, so molar mass of the gas, or mass of the gas divided by the molar mass of the gas. Okay, so we have here the chlorine. Okay, so we have here the chlorine. So, number of moles. So, number of moles is symbolized as the symbol of number of moles is in N. So, what is the number of moles here? Okay, so we have 10 grams of chlorine and the molar mass of that gas. Okay, so let's use the periodic table in order to find out the molar mass of this gas. Okay, so periodic table. So, we have here the chlorine. Okay, chlorine is over here. Alright, so chlorine is 35. Okay, 35.45. Okay, so 35.45. Okay, let's go back. Okay, so the atomic mass of chlorine is 35. Okay, so the molar mass of chlorine is 35.45. Okay, so 35.45. Okay, since we have okay, so since we have a molecular form of chlorine here, so diatomic form, so it means that this 35.45 will be multiplied by 2. Alright, so this 35.45 will be multiplied by 2, so we can have 35.45 times 2. That will be 70.9 grams per mole. Alright, so that is grams per mole. So we can cancel the similar unit that you have right here, so retaining the mole over here. So the answer here is 10 over 70.9, so that will be 0.14. So the number of molecules that you have right here, okay, so the number of molecules that you have is 0.14. So the N is equal to 0.14 mole. Okay, of Okay, it must be in a complete answer. Mole of Cl2. So this is the complete answer for this problem. Okay, so 0.14. Okay, so let's try to find out the argon that you have right here. Okay, so 34 grams of argon. So argon doesn't exist in a diatomic form. So we don't need to multiply it by 2. So again, in order to compute for the N, we need to have the mass of the gas, 34 grams argon, divided by... Okay, so what is the molar mass? So let's take a look at the periodic table. Okay, so the molar mass of the gas is 39.95. Okay, so we have it right here. So that is 39.95. Let's go back. Okay, so 39.95 grams per mole. Okay, so cancel the grams and we can get the number of moles or number of particles. So 34 over 39.95. Okay, so the N will be 0.85. Okay, mole of AR or argon. So that is your final answer. Okay, so next one we have the 18 grams of helium or hydrogen rather. Sorry for that. Okay, so 18 grams of hydrogen. So what is 18 grams of hydrogen? How many particles or how many molecules does 18 grams of hydrogen contains? Okay, so again, N divided by the mass of the gas, 18 grams of hydrogen. Alright, so hydrogen, as we all know, that is 1. Okay, that is 1 grams per mole. So times 2 because it is in a diatomic form. Okay, times 2, so we have 2 grams per mole. Okay, so 2 grams per mole. So we can have 18 divided by 2, that is 9. Alright, so we have 9. Okay, so the number of particles found in an 18 grams, alright, in an 18 grams of hydrogen is 9 moles of hydrogen. Okay, of that hydrogen gas. Okay, so for the fourth and final sample problem here, we have the xenon. Okay, fortunately enough for us that xenon do not exist in diatomic form. Okay, so we have N is equal to 45 grams of xenon over... Okay, so what is the atomic mass of xenon? Okay, let's take a look. Alright, so in this case, we have 131.29. Okay, 131.29. So let's go back to our calculation. Okay, 131.29 grams per mole. Okay, so what is the value of N? So we have 45 over 131.29. So that will be 0.34 mole of xenon. Alright, so that is our final answer. Okay, so I hope you did get this sample problem that we have right here. Let me know in the comment section what are the things that gives you difficulty in doing this. Okay, so I will try my best to answer those queries that you have. Okay, so if so, did you get the same answer as mine that I have right here? So congratulations to you if you got the same answer. Meaning to say that you understand how this formula, okay, how the formula in getting the number of particles works. Okay, so alright, so now that you know the different properties or measurable properties of gas, so let's take a look at the standard. Okay, that's the standard temperature and pressure. Okay, so we will be able to use this one in our discussion in the gas law. Alright, so in the next episode that we will have. So what is a standard temperature and pressure? So this is constant. Okay? When we talk about standard temperature and pressure, these are constants. Okay? So the standard temperature is always 0 degrees Celsius. Okay? So the standard temperature is always 0 degrees Celsius, and that is around 273 Kelvin. Okay? So that is the standard temperature. Now, meanwhile, the pressure, the standard pressure is 1 atmosphere. Okay? So if you will convert it into kilopascals, we have 101.3 kilopascal. And we have 760 millimeters of mercury if you will convert that in that unit. Alright. Now, the standard number of mole is 1. Alright. The standard number of mole is 1. And the standard volume, okay, under this temperature that you have over here, the standard temperature or the standard volume under 0 degrees Celsius, alright, the standard volume under 1 atmosphere, and the standard volume under 1 mole of that certain gas is 22.4 liters. Okay, so this is the standard volume. Okay, under this values that you have right here, under this constant value. Okay, again, the standard temperature is 0 degrees Celsius or 273 Kelvin. The standard pressure is 1 atmosphere. All right, the standard number of the standard amount of gases is 1 mole, and the standard volume, all right, the standard volume is 22.4 liters at following the standard temperature and pressure. All right, so these are again the conversion factors that you need to take note of. Okay, so in solving this conversion factor problems related to the measurable properties of gas. Okay, now these are the properties of gas. Okay, in summary. Okay, so gas properties can be modeled using the following things that we have right here. Okay, so we have volume, and the volume is always in liters. Okay, so take note, it is always in liters. If the value or if the problem gave you milliliters, then therefore you need to convert that one into liters. So we have temperature. Temperature, the standard value or the standard unit used in temperature is always in Kelvin. Take note, always in Kelvin. So if the problem gave you Celsius or Fahrenheit, you need to convert that one into Kelvin. Do not proceed with the calculations, alright? Do not proceed with the calculation in gas laws when the unit is in Celsius or Fahrenheit. Alright, so always in Kelvin. Next one, the pressure, it depends. Any pressure may do. Okay, any pressure may do. It can be an atmosphere, it can be torr, it can be pascal, it can be millimeters of mercury. It just depends on the problem. Okay, it just depends on the problem. So if the problem is asking you to convert each and every pressure that you have right there, then do so. Okay, you must be familiar with the conversion factor regarding pressure. Okay, so for you not to get lost. Okay, and finally we have the amount of gases. So N, it should always be in mole. So the unit of that is MOL. Alright, so mole, that is the amount of molecules present in a certain mass of your gas. Okay, so these are the properties of gas that we have right here. Now, what will happen if these properties interact with one another? Okay, this is just a preview of what is coming next, okay, for the gas law. So, volume and number of moles. Okay, so what do you think is the relationship between volume and number of moles? Okay, so you can write it down in the comment section below this video. Let me know, what do you think is the relationship between volume and number of moles? Okay, so as you can see here, as the volume increases, the number of moles that you have over here, the amount of gas also increases. It makes sense. In this case, it makes sense because when you inflate a balloon, once you put air inside that balloon, what happens to the size of the balloon? It increases. So when it increases, what happens? What happens to the amount of gas inside the balloon? Also increases. Alright? So as the volume of the balloon increases, the amount of gas inside that balloon also increases. So therefore, this is directly proportional. Okay, so let's take a look another interaction between these properties. So we have got the one that you have right here. So we have the pressure and then the volume of the gas. Right? So we have here the pressure and then the volume of the gas. So what happens? What happens when the pressure is less? What happens when the pressure is greater? What happens to the volume? So as you can see here, okay, so what is the relationship between pressure? Okay, so this arrow that you have right here, between pressure and volume. Okay, what do you think is the relationship? So write it down in the comment section below this video. Okay, so the relationship that you have right here is, as the pressure decreases, the volume increases. As the pressure increases, the volume decreases. So this is an inverse proportion. Okay, so this is an inverse proportion. So pressure and volume is inversely proportional to each other. Okay, so that's the two properties that you have right there. And okay, so that is all about the properties. Okay, so again, there are four properties. There are four measurable properties of gas that we will use in the gas law that we will have. So these are the following. Number 1, volume. Number 2, pressure. Number 3, amount of gas. And finally, we have temperature. Okay? And that ends up our topic for this video lesson. I hope you'll be able to get the value of the topic we discussed today. And if so, don't forget to like this video. If you have questions, suggestions, write them down in the comment section below this video. It will help me a lot in the algorithm for my YouTube channel. Most importantly, don't forget to subscribe to my channel and hit the notification bell for you to be updated for more science video like this in the future. I'll see you next time, everyone. Enjoy learning and practice always. Stay safe and peace out.
Baka みたい子供なのね